Hi, everyone. Welcome to this session of the P4 workshop. Today we have Pawel, Parol and Artur Jaworski from CodiLime to talk about how they've used ONOS and P4 on a SmartNIC to create an end-to-end network fabric.
Hello.
Hello.
Today we would like to say a few words about the solution that we have developed in our R&D department last year. This is a kind of proof of concept that mainly shows how to control a P4-Programmable SmartNIC with the ONOS controller. Let me start with a brief introduction of our company. CodiLime is a service-focused company that has been helping clients build and enhance their products since 2011. Software product engineering and network engineering are our core competencies. We build and deploy networking solutions for networking software and hardware providers, DC providers, ISPs, telecoms, and startups of all flavors. Okay, so first, I will list the key components and technologies that we use to build our solution. So the main data plane component within our setup is a P4-Programmable SmartNIC that has been installed in one of our bare metal servers. We used a card offering a native support for P4, and it was a Netron Magilio SmartNIC with two 10G interfaces and the NFP chip on board. This card is controlled effectively by a well-known ONOS SDN controller in our setup. However, to make this possible, we developed some code. We'll talk about this in a moment. What is also important is that the scope of our POC is actually a bit broader than just the integration aspects related to ONOS, SmartNIC, and P4. What we also wanted to show is that a single SDN controller like ONOS can control a heterogeneous data plane consisting of different components that use different protocols on their northbound interfaces. That's why we connected our SmartNIC to some kind of emulated leaf-spine fabric based on OVS software switches and to some end hosts running in Docker containers. And what is more, we believe that this approach, with this approach, we provide some kind of end-to-end perspective in our setup. Now let's take a look at the high-level architecture of our solution. The main role of the SmartNIC here is to perform certain network functions that would normally be implemented as VNFs or CNFs deployed on the same server that SmartNIC is installed. And this is actually called an offloading. To demonstrate this, we have prepared an example implementation of the Firewall network function in P4. But this is only an option. Other functions such as load balancer, NAT, or anything else can also be executed on the SmartNIC once the relevant P4 implementations for them are prepared in the future. As I mentioned earlier, there's also an emulated leaf-spine fabric based on OVS instances here. Both the SmartNIC and leaf-spine fabric make up the data plane of our setup, and they are controlled by one ONOS instance, but using different protocols. OVS switches are controlled using OpenFlow, since ONOS offers native support for this. On the other hand, controlling the SmartNIC with the ONOS is a bit more complicated. Normally, ONOS controls P4 targets using P4 runtime protocol, as we know. Theoretically, the version of the Netron Magilio SmartNIC SDK that we used also declares support for the P4 runtime, but it is not actually fully supported. We'll talk about it later. So it turned out that a direct integration was not possible in our case. But there is also another method of controlling this card at runtime, and it is based on drift. Therefore, to make integration with ONOS possible, we created a dedicated SmartNIC Proxy application that converts gRPC-based P4 runtime to drift-based manufacturer's protocol, and thus we achieved our goal. Okay, so now let's start going through the different elements of our setup one by one. Let's focus first on the SmartNIC and our P4 program. We implemented a firewall function on the SmartNIC based on the V1 model, which is supported by the Netron Magilio card. And this implementation is very simple. As you can see in the parser block, we define first the limited number of headers we can operate on. And in fact, all the logic of our firewall is in the ingress block, where we defined two tables. The first one performs a very simple forwarding mechanism with the lookup based only on an input interface ID. And the second table is the actual firewall table, where matching to some set of different headers fields takes place. For a given packet, we can perform one of the two possible actions, which are allow or drop. And finally, we have the parcel block that is responsible for reassembling packets. Now let's take a look at how the leaf-spine fabric is configured. It contains 2 spines and 4 leaves. Each of them is an OVS instance, and the topology is created using the mininet utility with a dedicated Python script. Additionally, there are emulated hosts connected to the data plane network just to generate and receive traffic going across the data plane. So we've got 3 end-user instances and 2 hosts acting as application servers. The general idea behind this setup is that end users, labeled here as host A, B, and C, will try to access the services available on the application servers. From the IP forwarding perspective, we've got 3 different subnets here. The first one is a dedicated subnet for the application servers, and they are connected to the fabric through the SmartNIC, as you can see. And the other 2 subnets are for end users. Since we've got more than just one IP subnet configured on the leaf-spine fabric in our setup, we need to somehow handle IP routing there. And for this purpose, we decided to use one of the applications offered by ONOS just out of the box. It is called Simple Fabric, and it just provides a simple routing between subnets connected to different leaves. So it perfectly meets our requirements in this. And this is how it looks like on the physical level. The entire setup is deployed on 2 bare metals. The first one has the SmartNIC with 2 10G Ethernet interfaces installed. And the second one hosts all other data plane and control plane components of our setup. All emulated hosts and the mininet with a leaf-spine topology are running in Docker containers. And to enable interconnection between all these components, some common Linux network techniques and objects are used, such as Linux bridge instances, if links, etc.
Now let's take a closer look at the SmartNIC Proxy application that we developed from scratch in our R&D department. Now we'll try to explain why we built this adapter. As we know, ONOS controls P4 targets using P4 runtime protocol. Netronom also declares support for P4 runtime for the Agilio SmartNIC. Additionally, Thrift-based manufacturer's protocol is supported. So there are 2 ways to control the SmartNIC at runtime. So since both the SDN controller and the P4 target support P4 runtime, our natural choice was to use it to accomplish communication between data plane and control plane. But after first try, turned out we were not able to have a working solution. Since the P4 runtime version implemented in ONOS and in the SmartNIC were not compatible with each other. Then our next step was to downgrade the P4 runtime version in ONOS. But that unfortunately didn't work either. Additionally, we noticed the RTE software dedicated for Agilio SmartNIC that we received from Netronom had some limitation if P4 runtime was used. For example, it was not possible to use ternary matching. Also, packet out mechanism was not implemented. As you can see, it was not possible to use P4 runtime according to our expectations. Only Thrift-based protocol offered the capabilities to control Agilio SmartNIC at runtime in a proper way. Then we started to think how to deal with it. There is a Thrift-based protocol supported by SmartNIC, but the ONOS soundbound layer does not contain it. So we made a decision to implement a SmartNIC Proxy, which would convert P4 runtime to Thrift-based protocol. How does it work? ONOS populates firewall tables using P4 runtime protocol. The appropriate messages are accepted by the gRPC server implemented within the SmartNIC Proxy application. The data is then repackaged into the Thrift-based manufacturer protocols and sent to SmartNIC. This is how the SmartNIC Proxy application works. This makes communication between ONOS and SmartNIC possible. But of course, that's not all. Because in order to effectively control the firewall behavior implemented in P4 on the SmartNIC, you need to create the appropriate logic at the ONOS level. And this is done by our custom control plane application. This application contains several different function elements. Basically, we can distinguish two main parts of our firewall application: the pipeconf and the control application. In ONOS, a pipeconf is a kind of service to manage the configuration of protocol-independent pipeline. Within a pipeline, three different types of components can be distinguished: modules, behaviors, and extensions. As we know, this is a kind of convention that is used in ONOS. In short, the idea to use this convention to describe your custom pipelines in such a way that is understood by ONOS. The control application, in turn, is an actual control plane for firewall implemented on the SmartNIC. It is a pipeline-aware app, meaning that it is dedicated to a particular data plane. There is a firewall service component here, the main task of which is to manage and apply rules for P4-defined devices. Our control application also includes a fully featured user interface that offers a graphical user interface and a command line interface. Our graphical user interface is actually a kind of extension to the standard ONOS web UI. It contains a table of firewall rules that reflects the current firewall state on SmartNIC. The user can easily add new rules or delete. The CLI component, in turn, extends the native ONOS CLI with some firewall-specific comments. It offers the similar capabilities as the web UI component, and it is targeted at those who prefer to work with CLI rather than GUI. And here is an example of how user-made firewall table were mapped to traffic flow related to SmartNIC at ONOS level.
Now let's take a look at the very brief demonstration of our solution. We would like to show you two example scenarios of how the firewall application can be used within ONOS. We have two very short videos prepared for this purpose. The first one is about inserting some TCP-related rules to the firewall deployed on the SmartNIC. An instance of the HTTP server is running on the server 1. It is based on Nginx, and it is listening on 10 TCP ports, as you can see. In the zero config state, host A and host B can access the service without any issues. In the first step, we'll block traffic coming from the IP subnet, which includes host A and host B, but only for one TCP destination port value. Next, we'll add another rule to the firewall to block a certain range of TCP destination ports, but only for host B. We'll perform all these steps using the web UI component of our custom ONOS control plane app. So now we'll add another rule to the firewall table. First of all, we need to specify an action, which is deny here, and then IP proto field. We'll set it to TCP. We'll provide the subnet for the IPv4 source address field and the IP address of the server 1 for IPv4 destination address. And of course, the value of the TCP destination port to be blocked. So now we can see the rule has been applied, and it is injected to the firewall on the SmartNIC. And as we can see, host B and host A cannot access the service on the server 1 when they are using that TCP destination port that has been blocked. And there's no impact on host C, which is okay. And now we'll add another rule, but this time only for host B, so we'll provide the right value of IPv4 source address, and then we'll provide the range of TCP destination ports from 9056 to 90. Now we need to wait a couple of seconds for optimization. And yes, it has been applied. And now, as we can see, host B is trying to access the service using one of the ports from the range that has been blocked. Also another port from this range, and the effect is exactly the same. And for host A and for host C, there is no impact. This is according to our expectation. Now it's time for the second scenario, which is very simple. In fact, we'll block ICMP traffic from host A to the entire IP subnet where the application servers are located. As a result, we expect host A will not be able to ping either of the two servers. And then we'll override this rule with the totally opposite one so that we'll allow for such kind of traffic again. But this time we will use an ONOS CLI with our custom extension dedicated for the firewall service. So maybe first of all, we'll check if host A can ping the service 1 and the server 2. Yes, it is possible. And then we'll access the ONOS CLI, and we'll make use of our extension dedicated for the firewall service. So maybe first of all, we will list the current status of the rules which are injected to the SmartNIC. And now, by invoking the firewall add command with some parameters, we'll provide another rule to the firewall. So we'll specify the right values for IPv4 source address and destination address, just according to our scenario. Provide, of course, the right value for IPv4 proto, ICMP in that case, and we need to specify the action which is deny in this case. So we can see now that the rule has been added successfully. And now let's check the impact on host A. So we can see that host A now cannot ping server 2, cannot ping server 1 as well. So it is exactly according to our expectations, and there is no impact on host B and host C. Okay, so now, as I said, I will provide just totally opposite rule to our firewall service, just to override the previous one. So the only thing that we have changed is action specification from deny to allow. And as we can see, host A can ping server 1 and server 2 again. Okay, if you think you would like to know more technical details about our solution, you can watch the webinar we recorded last year. So here's the link. Okay, so this is the end of our presentation. Thank you for your attention. Now we are happy to answer your questions.
Thanks, guys. That demo was awesome. Now it's time to do a little bit of Q&A. I've had a chance to take a look at the video and gotten a few questions from folks that also have had a chance to look at it. And let's get started. So the first question is about the proxy. So first of all, I want to say it's a pretty clever way to link between two systems where you have slight differences in the protocol. It's something that we've used at ONF and throughout the industry, for example, in Volta, to adapt between things like OpenFlow and the OLT APIs. But just a quick question: could you explain a little bit more about how you built it, what technologies went in here, and what that component looks like?
Yeah. So maybe first of all, I can admit, at least to some extent, that Volta could be considered a kind of inspiration because we had some experience in Volta because I had some experience previously with OpenCord and some solutions which were based on CBA. So I could touch a bit the solution, a kind of reference design, and I knew that there is something like Volta there. So as a kind of introduction. But in fact, the idea of providing the adapter just came to practice, let's say, because of the fact that we couldn't connect ONOS to the SmartNIC in the proper way using the P4 runtime protocol, because the versions of the P4 runtime on the SmartNIC and on the ONOS were not compatible to each other. And that was the main reason. So we're struggling a bit. We are trying to find a good approach of how to deal with that. And we were trying with different solutions, downgrading, as we presented during the presentation, of downgrading the version of the P4 runtime at ONOS, but it didn't work. So then we decided that since the best way to steer and to control that card at runtime is Thrift-based manufacturer proprietary protocol, maybe it's the best idea just to use it somehow. But for that purpose, we decided to prepare a kind of intermediate layer, and that's why we decided to build a proxy. So that's the main reason. I don't know if it does answer a question.
No, thank you. So in terms of that layer, is that something that you intend to keep proprietary to CodiLime, or is that something that you want to work with the community on?
So in fact, we use a kind of proprietary Python API within the southbound layer of our proxy, because after we got the card from the metronome, we receive also some kind of RTE, which is a software to control this card, and those Python APIs were reused in our SmartNIC proxy. So this is the main reason that we cannot make it public, because you know how it works.
Yeah, sure. Makes sense. Cool. So maybe moving up the layer of the stack a little bit. I noticed that when you said you had two choices, you could go with the pipeline specific application, which appears to be the choice you took, versus a pipeline independent approach where you implement a pipeconf. Did you have a chance to implement the pipeconf as well, or is that something that wasn't necessarily inside the scope of the project?
Artur, you'd like to answer?
We actually built the pipeline or protocol dependent pipeline, application for our firewall, like it was presented on the presentation, to manage the firewall rules on a SmartNIC. Okay,
thanks for the answer. A couple questions about the P4 that you have and the interface, the table interface that you have. So the first thing is, it looked pretty cool, the ability to support the high-level range construct for TCP ports. How is that implemented in your pipeline? Do you use the P4 range construct, or is there some high-level range to lower-level entry mapping that you're performing?
Actually, it was working like we splitted all the rules to all the rules for the firewall. We split it into I don't remember how it was called in ONOS. Pavel, do you remember?
I don't know what you mean right now.
So I guess the question is, in the first entries you were putting, you had like specific TCP ports that were going to be blocked. And then you inserted a range entry where you said from 56 to 60, we're going to block a range of.
Yeah, so this has been, let's say, split it into separate singular rules for any kind of TCP port independently. In fact, so there's a kind of set when you're looking at the application level from the user's perspective. But in fact, the underlying logic is like you're putting the independent rule for each TCP port, as far as I remember. Correct me, Artur, if I'm wrong, but I guess this is the way that we did it.
Yeah, it was actually, I remember now, it was split to a singular flows. Each range was split to a singular flows for each ports.
Got it.
And it was converted to, I think, to a range on a card.
Got it. Cool. Thanks. And it looked like also towards the end of the demo, you had a block rule and then you overrode that block rule with an allow rule. Is there a general like allow before block policy, or is it last writer wins? How do you manage the conflicting rules where one rule wants to allow and maybe a different one wants to deny?
All the rules which you put first had a bigger or last rules had the biggest priority.
Okay, got it. So you manage the priority kind of under the covers for the TCAMs.
Yeah, actually, it's a little bit funny story because our SmartNIC didn't support priority for a P4 entries in tables, so we had to after each rule was added, we need to clean the card from all the entries and re-add them in a proper sort order. Yeah.
So that's why you see all the little check marks go each time there's an entry being added. I see. Got it. So that sounds like it's maybe something that can be fixed on the SmartNIC SDK side, right?
Yeah.
Got it. Okay. Are there any challenges that were particularly kind of interesting or fun from a technical perspective you encountered when
I think the biggest challenge, as we said, was in fact developing a kind of intermediate layer between ONOS and SmartNIC just to make any working solution to connect these two things together. So this was the biggest challenge, and on the other hand, it was also the biggest fun, I guess, because if you're making a lot of steps and at the end of the day you realize, yes, you did it. So you're happy and you know that it's worth working on that in a way that you succeed. And in general, what I wanted to stress here is that our solution was not about any kind of optimization in general sense. Our solution was more about the feasibility, and this is the very important thing, because what we wanted to accomplish, in fact, was to first of all connect the SmartNIC to ONOS. To the best of our knowledge, this was one of the first setup, such kind of setup, because I haven't heard about something similar. I know that there is some approach of connecting Intel PAC N3K card to ONOS using Stratum, but this realized in a totally different way, as far as I remember, because this is about providing a particular Docker container with Stratum to the server that hosts the card. Of course, there are some tricks that has to be done before, like compiling the P4 to the right FPGA, bitstream or whatever. I don't remember how it works, but I guess that is more or less something like I'm telling you right now. Correct me if I'm wrong. Maybe you know more about that. But our approach was totally different. I think that it is more general, because if you have some device and you have some SDN controller, not necessarily ONOS, but any kind of controller, providing an adapter, you're able to interconnect those two words in a general way. Of course, this is about converting one protocol to another. So this is a way that it could work, and we had a proof, let's say, that it can work like that. So this is the general idea, but our setup was in fact something was about something broader than only connecting P4 SmartNIC to ONOS, because we wanted to show that single SDN controller like ONOS can control a heterogeneous data plane using different protocols. And that's why we added also this part with emulated OVS based leaf spine, just to emulate somehow the real behavior of a simple data center or whatever. And also we added some Docker containers just to provide a kind of end-to-end view to our setup. So in fact, our setup is about two things: the integration aspects between SmartNIC and ONOS, and just to provide a kind of single SDN control over a heterogeneous data plane. And this is how we approach that.
Yeah, that makes a lot of sense. And the heterogeneous aspect is a really powerful message, I think, because in any network, there's going to be a variety of devices, protocols, types of devices, et cetera. So
yeah, exactly.
So having a solution that works across all of them and can coordinate your network topology makes sense.
Frankly speaking, if we are considering networks in, let's say, a very wide manner, meaning that there are different domains, I personally do not believe that a single SDN solution can control all the things just from one point, because it's very difficult, especially if we are considering different FCAPS issues. These are very specific for a particular domain. These are different for access, for transport, for IP routing, for radio stuff, whatever, for optical access. This is not the same things, and this is very difficult to combine in one SDN solution that controls everything. But when we are talking about some, let's say, limited deployment, like internal network in a DC, here, I do believe it is possible to have something which controls all the data plane. And that's why those heterogeneous aspects of the control are important from our perspective.
Got it. Yeah, and getting into that a little bit more. So if we look at a data center or maybe some other topology, do you see the SmartNIC playing a role as serving kind of as a gateway from the data center to an external network? Do you see it running on every server, so you have some programmable capabilities between the CPUs and the network, or do you see it as an intermediate middle box maybe that you run traffic through? What's your vision, or where do you see this going?
So I would say this a little bit about edge computing, but maybe not such kind of edge computing that we understand as a kind of approach that we've got some centralized data center, and there are also some edge places where the edge computing takes place. It's not the same. Maybe this is a kind of paradigm, but this has to be used in a little bit different manner in a DC, because I believe that imagine you've got a kind of VNF, a centralized VNF in your DC, which is launched or on some server in one particular place. Then if for some workloads between CNFs or VMs hosting VNFs in this data center, or hosting whatever, in fact, if we consider this particular network function, which is launched in a centralized way as a kind of part of your service chain, then you can approach a kind of tromboning effect for some of the workloads. If you consider the approach like the routing is being deployed in the open core, like we have a distributed router on the leaf spine fabric, this is a kind of distribution, and from the optimization aspect, it could provide a kind of benefit to you, a lower latency, etc. And going kind of further, meaning that deploying some parts or some network functions on the SmartNIC, which are hosted in a bare metals, can be even a better level, a higher level of optimization. Of course, there are some limitations for that approach, but in general, I believe that SmartNIC can be a kind of edge computing inside the data center. I know that it may sound strange from the first sight, let's say, but I think it is possible. It is possible, and it could provide some benefits.
Cool. Yeah, that makes sense. And maybe my my last question for you today is around path to production or production feasibility. What's left before this is ready to deploy or put in a customer network.
So our intent was not to provide any kind of commercial product by doing this setup. It was just to show that some things are possible. Because we do not provide any kind of products which are based on SmartNIC right now. Our company is more focused on services because we offer a very big variety of professional services to our companies, which are more or less related to the networks and deal with networks. So this is a kind of another skill set, let's say, that we can help them, especially when we are talking about a very interesting trend, which is low-level programming right now, because a lot of our clients are asking for DPDK, for SmartNIC, for FPGA, for P4, for some kind of optimization based on eBPF, let's say. So these are the things that are in very big interest of some companies. So this is a kind of proof, okay, you can work together with CodiLime. We can help you because we have some experience with that. Here is the proof that we did something.
Cool. Yeah, that makes a lot of sense. And from ONF side, we're seeing sort of very similar interest in kind of a broad spectrum of targets, whether it's running on the CPU, SmartNIC, FPGA, ASIC, programmable, fixed, whatever. So yeah, I think having that skill set and building this up, putting these demos together, super valuable. It's fun to see, fun to watch, and hopefully, you're another strategic player in the space that people can come to and rely on to get these things deployed.
Okay, Brian, many thanks for these words. We really appreciate that you enjoyed.
Yeah, thanks again for your time and putting the demo together.
Thank you so much.
Thank you.